Welcome to the second video of the three-part Socket Reuse video series. In this video, we will continue our effort to build a socket reuse-based exploit. We will focus on examining the low-level internals of a socket and how it can be translated into shellcode. Let's start by examining the construction of a socket from a debugger perspective so that we have an idea of what we will try to reuse. As we require a function that is responsible for receiving data, we will use the receive function. However, in order to use a function, it requires supplying proper arguments. The receive function will be used to receive the next portion of data during runtime. For example, if we call the receive function once again at the beginning of the A buffer, the data will be written here, right after the A buffer, so the execution will not be interrupted, and the second shellcode will be built during runtime. Here's the official Microsoft documentation of receive functions. It takes 4 arguments. First is a socket, that is the file descriptor to the socket. We will reuse the current descriptor of the current socket. Next is the buffer pointer, the address of the area where we would like to receive the data. In our shellcode, this will need to be set up to an address after our shellcode. Then there is the length of the buffer we would like to receive, which is self-explanatory. And finally, we have the flags, which we can leave equal to 0. Let's now check out the receive function in action. We'll restart the application and navigate to the second default breakpoint, which is placed by the debugger at the application's entry point. Let's scroll down the disassembly dump to find the call to receive function. In bigger software, this could be a challenge. Additionally, there could be lots of calls to the same function. With Vuln Server, this should be fairly easy. Here we can see a call to the receive function. We suspect that this is the one that is responsible for receiving user commands. Let's click it and press F2 so as to place a breakpoint at the moment of the receive call. We can see that before the call to function, several operations take place. They are responsible for pushing certain arguments to the stack. Let's try to see it on a live example. Let's run the application and see if the receive breakpoint is hit after the exploit is launched against the Vuln server. We are right before the call to receive function. The debugger has already guessed some arguments to the function based on what is on the stack. The first argument is the socket, or to be more precise, the file descriptor of the current socket. Next is the buffer address, buffer length, and the flags, which are null. Our goal is to achieve the same setup that is currently on the stack, but with one difference. The buffer pointer has to point to our buffer that is sent within the exploit. Let's see how we can achieve this. Of course, the address of the buffer is different each time, so we will need to generate it in runtime. Also, we will need to dynamically retrieve the socket file descriptor, as it might change among subsequent runs of the software. While buffer length and flags are pretty easy to set up, let's try to figure out how we can set up the dynamic value of the socket and buffer address on the stack. While we're still paused on the breakpoint, let's right-click on the buffer address that's located on the stack and follow it in dump. we can see that this area is currently filled with zeros. Now, let's use the step over function. The difference between step in and step over is that step in brings us to the next subsequent instruction, even if it's inside a function to be called, while step over allows us to skip whole function calls as they are executed in the background, meaning we don't need to watch every instruction contained within them. Let's choose step over so that we can see the application state right after the receive function finishes. We see that the buffer was received by the application. We can also see the whole payload that was sent in an unmodified form in the place where the socket buffer pointed to. If we now allow the application to run, we can see that the buffer disappeared. Apparently, the application performed some kind of operation on the data. While the payload data was received in proper form, due to the internal processing of the payload, it is being moved and modified. However, since we just saw that the receive function can receive the whole buffer, this is great as it's the only thing we need now. The address of the buffer is different than the current buffer address. This is proof that the payload was moved and processed by the application. Let's now restart the program and relaunch the exploit. The execution started at the receive function call. We can observe that the address of the buffer is different. Regardless, the socket file descriptor is still the same, and we should remember that this is not a constant value. Let's focus first on examining the location where the socket file descriptor is stored. While we cannot hard code this address, maybe it is held in some location within the application memory that can be referenced relatively. If during a crash there is some accessible location that holds a reference for the socket, we might be able to use it. Now let's examine the instructions that are executed directly before the call to receive. As the socket is on top of the stack, it means it has to be pushed as the last argument before the call to receive. Those two lines are responsible for pushing the socket descriptor value onto the stack. First, the value is stored in EAX, and then it is moved to a location on the stack. So we are interested in the address accessed in at the first of those instructions. Let's go to the dump window and press Ctrl-G. Now we'll type the address where the socket is initially being retrieved from. We can see in dump that the current socket value matches the memory contents of that place. Let's continue the execution while having this location open in dump so we can see if any changes are applied to it when the crash occurs. Now let's press run. Even if we subsequently step in and the overflow occurs, the socket identifier is still in the same place. This address was retrieved relatively close to EBP. Can we also retrieve it at the time of the crash? Let's check the address of the socket file descriptor. It starts with 1AC, which is close to the current stack pointer ESP. This might possibly be the reference we are looking for. In order to confirm that, we will use a calculator to count the offset from the current stack pointer to the address of the location where the socket file descriptor is stored. Let's start the calculator in programmer mode and hex mode at the same time. Now, copy the address of where the socket is stored and paste it into the calculator. Next, we'll subtract the current stack value from it. For convenience, it also can be copied from the debugger. The result is 188, and we should also take note that this is a hex value. We will want to remember this for later. Now, let's restart the application. We will also run the exploit again. The socket value is still the same, so let's move on. We are currently at the moment of the crash. Let's step in so we are at the beginning of our A buffer. In the dump window, let's press Ctrl-G again, or we can choose Go to Expression manually. We will try to access the value that is 188 hex bytes away from the current ESP. We see that we can reliably find the socket reference at that address. We have collected almost all required information that is needed to rebuild a receive call. At our breakpoint, reference to receive is held. We also know that ESP plus 188 hex holds a reference to the socket at the moment of the crash. The address of the buffer can be retrieved during runtime. For example, the current ESP can be pushed and modified to a point a bit after the address that is currently executing instructions so that we receive the data right after our shellcode. The buffer length and flags are not a problem, as we just need to push some fixed values. In this video, we took a look into a socket's internals. In the next and final video, we will incorporate it into a working exploit. And this concludes part 2 of the Socket Reuse video series. Thanks for watching.